Hello and welcome to Wednesday's recording. This is a recording to finish up Unit 3, Lesson 1. So in Monday's video, you learned how to identify special segments and lines and circles, including radius, diameter, chord, secant, and tangent. You were also able to explain two circles with the same radius are congruent. And in yesterday's recordings, you were able to use properties of lines tangent to a circle to solve problems. So our last learning objective will be today. And today we will identify common tangent lines, including common internal tangents and common external tangents. So let's start with some vocabulary words. So we have two diagrams here, each containing two circles. And we can see that lines can be tangent to more than one circle at the same time. And common tangents to two circles may be either internal or external. So a common internal tangent intersects the line segment containing the centers of the two circles. So if we look at the diagram on the left, we see circle A and circle B. And I've highlighted the segment connecting the two circles, the two centers of the circles. And so you can see that our tangent line, this line in blue right here, intersects circle A at exactly one point and circle B at one point. And it also passes through the dotted line, or the dotted segment that joins the two centers of the circles. When this happens, this is called a common internal tangent. It passes between the two circles, crossing over that segment connecting the two centers. On the right-hand diagram, we see circle A and circle B with another tangent line, so the line still intersects circle A exactly once and circle B exactly once. But you can see it does not pass through the segment joining the two centers of the circle. This we refer to as a common external tangent. So now let's practice identifying common internal and common external tangents. So here we have a diagram with circle D and circle C, and I have drawn in a dotted line connecting the two centers. We want to see how many internal common tangents are in this figure. So remember, common internal tangents are the lines that intersect each circle exactly once, but pass through that dotted line. You can see that this line right here is tangent to both circle D and circle C, and we can see their points of tangencies are here and here. So this would be one internal tangent because it passes through the segment connecting the centers of both circles. We also see one more common internal tangent, and that would be this line right here. We can see it's tangent to both circles, intersecting each at exactly one point, and it crosses over the path connecting the two centers of these circles. So we have two common internal tangents in this diagram. In the next question, we want to look for common external tangents. So again, I can draw a dotted line connecting the centers of these two circles. And we want to look for the lines that are tangent to the circles but do not pass through that dotted line. And so here we see this one and this one. So here we have two common external tangents. So now that we've gone over some vocabulary, what I want to do is I want to show you an example problem involving both common external and common internal tangents. So let's start with an example using common external tangents. So in this diagram we have two circles, circle A and circle B. Again, we name the circles by their center points. We want to find the distance between the centers of these two circles. So I'm going to draw a line connecting the two centers of the circles, B to A. That's the distance that we want to find. What I'm also going to do is I'm going to draw in a line perpendicular between the two radii of the circle. So from point A, I'm going to draw it straight across, perpendicular to radius BC. And I'm going to label that point E. So we can see in our diagram we have two radii. We have a radii of circle A measuring 15 inches and a radii of circle B measuring 25 inches. Now what we can see is that I have this small portion of radii BC, and I have the entire radius measuring 25. I can see that the figure, and let me choose a different color here to illustrate this. Let me use green. You can see that I now have a rectangle ADCE, and so if DC is 40, then so is this segment down here. This is 40. And the entire radius of BC is 25, so I can find the length of BC right here. If I take 25 and I subtract off this length of radius DA, because this right here is also 15. So 25 minus 15 tells me that just the part from point B to point E is 25 minus 15, or 10. And so what I'm going to do is I'm going to pull out this small right triangle so that we can see exactly what's going on. So I'm going to just redraw this over here. And I'm going to label it so we can see the points. So here we have circle center A, here center B, and here we have point E. Now I know A to E is 40, just like in the rectangle above, and EB is what we just calculated to be 10. So now I have a right triangle, triangle AEB, and I can now use the Pythagorean theorem to solve for the distance between the two centers. And so remember, the Pythagorean theorem is A squared plus B squared is equal to C squared. So this is the Pythagorean theorem. And I know the two legs of my triangle must be A and B. So this A, this B, again, they can be interchangeable. And I'm looking for the distance between the two centers of the triangle, this line right here, which is our hypotenuse. So let's plug these values in. I can say that A is 40, so we have 40 squared, plus B is 10. So 40 squared plus 10 squared is equal to AB squared. So all I did here was use substitution. And now if I simplify this, 40 squared gives me 1600. 10 squared gives me 100. And AB is just the sum of those two values. So adding 1600 and 100, or adding 1600 plus 100 gives us 1700, and that is the length from A to B squared. So to figure out what just AB is, I need to take the square root of 1700. And doing that, I get about 41.23. And so that is approximately the distance between points A and points B. And that would be in inches. So now that we've seen a problem using common external tangents, let's move on to our last problem, which is involving common internal tangents. Now I'm going to have to stop this recording and start another one. I'm on a time limit with the program I'm using. So stay tuned for the next short video. We're going to do one more problem showing an example using common internal tangents.